known Chris a long time, and he has been part of the development of metabolomics. He was the founding scientist, if I got the term correctly, at Metabolon.
Yep.
And in 2010, he moved to other things and was part of both the Michigan Regional Comprehensive Metabolomics Center and also the Florida Regional Metabolomics Center, CCHEM. And he's been specializing in what we hope is a bit of a breakthrough in metabolomics, which he's going to tell you about today, which really takes us from doing discovery into the quantitative science that everybody really wants to do. So it's not just a matter of finding out unusual things, but also measuring them and making sure that you measure them today, tomorrow, and next year the same way. Is that a good enough intro?
That was great.
Okay, I'll let you have the rest.
Thank you very much, Steve. I look forward to coming there sometime. I'm sorry I couldn't come today. I am suffering a little bit of a cold, and I will apologize now if I am forced to cough or anything. I think some of you may be in the same boat, but it's a pleasure to talk to you about IROA. I hope that you are all sufficiently interested in metabolomics that you seriously think about the possibility of using it. And as part of this talk, as Steve said, you know, he and I have been in metabolomics from the very beginning. The word metabolomics didn't show up in the literature until 2001. And, you know, we were both there in '98. We called it something different, but it was the same real thing. And it had flaws. It has the same flaws that genomics did in the early days, that proteomics did in the early days. And we're learning quite a bit. And what today's talk is all about is about how we have learned to overcome some of these flaws. So what is IROA? IROA is an attempt to repair many of these flaws. IROA is a series of protocols that are based on isotopically specified patterns of peaks in the mass spec that embed specific chemical characteristics into the mass spec data stream. And these are mathematically definable isotopic patterns. And so, you know, these patterns are defined by nature, by the nature of math, they're fundamental. And because they're absolutely fundamental, they're inherently extremely stable. They don't rely on anything other than themselves. Once you've embedded information into the mass spec data stream, then you all of a sudden have a tremendous amount of additional stuff that you can pull out and use to your advantage to get higher quality data, to dramatically reduce error, and to get yourself the lowest possible experimental variance in quantitation. And you know, and these things come at, you know, they're trivial to do, and they come at virtually no cost. You know, I mean, they're nothing compared to, you know, to normal things. So how do I talk to you about, you know, about the IROA signal? It's this way. If there was no C13 in the world, then the molecule arginine shown here, and I believe you can see my mouse, so I'm hoping you can.
Yes.
Arginine has 6 carbons. If there was no C13, then all of those carbons would be C12. And if all of those carbons were C12, the mass of the monoisotopic peak is 175.1190. And that is the only peak that every molecule would have. But in reality, the natural abundance of C13 has 1.1% C13. So there is a random probability that each one of these carbons will have a C13, and the probability of that is 1.1%. So what that means is that in reality, when you look at arginine, the same molecule, you see the peak at 175.1190, and it is by far the dominant peak. But you see this little tiny peak at 176.1223. And that represents the population of arginine molecules that by chance contains one and only one C13. And that peak is actually so small that for most of my career, I ignored it. And most people do. Whether they tell you they do or they don't, they usually do. So here we begin a thought experiment. What if rather than 1.1%, we kicked the probability up to 5%? So we now say that in the molecule arginine, every one of these carbons now has a statistical probability of 5% in each one of those positions of being a C13. When that happens, all of a sudden you get a very significant rise in the M+1. This M+1 is now 31.2% of the height of the monoisotopic peak, the peak that contains only C12s. And what's more significant is that this, because this is a simple probability theorem, then the calculation of the height of this peak, the M+1, relative to the monoisotopic, is trivial. It's a little, in its exacting form, it will tell you exactly that it's 31.6% of that. But if this is 6 carbons at 5%, and so you might intuitively think that it's about 30%. And if you think about that, that means that you would intuitively think that 5 carbons would be 25%. It's really 26%. 4 carbons would be 21%, etc. And so it's a step function. The height of this peak will tell you the number of carbons. Exactly. And that is absolutely true. That thought experiment plays through to perfection. And the math plays through to perfection. And once you understand the math and you understand the thought process, then you now say the reverse. What happens if this was 95%? Well, at 95%, something very different happens. The vast majority of the molecules contain only C13s and do not contain any C12s. And so the monoisotopic is now 181.1396. You don't have to remember these numbers, just the general principle. So the monoisotopic is 181.1396. But now when it's diluted with a C12, which weighs less. And so it's now, rather than having an M+1, it has an M-1. And that M-1 is at 180.1363. And it has an M+2 and an M-2. And so the math is going to dictate what the shape of this collection of peaks is. And it's always a collection of peaks. We tend to focus on the height of the M-1 and M+1 because they tell us the number of carbons. But the math on this side is exactly the same. This one is a step function. The M-1 is a step function of the number of carbons. And so it very exactly and always tells you the number of carbons in the molecule, provided you know the isotopic abundance that you're calculating it for. And so this is just a little mathematical reality. Now let's bring it to practicality. If we were to create a world in which 5%, all of the experimental molecules contain 5%, and so that all of the biological molecules contained patterns that looked like this and were calculated specifically in this way, and we grew up a series of internal standards which had the pattern like this, then we would have a triply redundant system, because we have a system where the distance between the 175 and the 181 is the mass of exactly 6 neutrons. The height of this is telling you it's 6 carbons. The height of this peak is telling us it's 6 carbons, and the height of this peak is telling us it's 6 carbons. When all 3 of these are in agreement, the probability that it's wrong is vanishingly small. There is virtually nothing that could, randomly produce a pattern like this. So this is, from an informatics point of view, this is an extremely strong signal. And you can pull these signals out of noise, and again, it's the strength of the pattern and the pure mathematical basis of the pattern that make it as strong as it is. Perhaps even more important than that, though, is what I said a second ago. We've set up the experiment so that all of my biological molecules in the experimental side have a C12 pattern that looks like this. And the C13 internal standard has a pattern that looks like this. But then all of the things that do not have that pattern are noise. They're garbage. They're things that we see in the mass spec, and we see a lot of peaks in the mass spec. And I'll show you a very simple experiment in a few minutes that will prove to you that, basically 74% in the sample set that conservatively, 74% of the peaks that are seen in most mass specs are artifacts. They do not come from the experimental system that you are that you are trying to analyze. They're just fake peaks, and they confound the issue every single time. They confound your statistics. They give you bad data. Who needs bad data? You encode the information systems into the data, and once you encode the information systems in, then you never get it wrong. You've got very strong data. You've got much better data. This is what we get used to seeing. So we see these peaks in the mass spec all the time. They are, this is a 9-carbon peak, so the pattern is physically different from the patterns that I was showing you, but it's absolutely mathematically accurate. And again, not to make the point too overbearing, but only a molecule of biological origin can show this signal. Artifacts can never show it. So you can completely, by following these signals, you can completely get rid of, of non-data, of false data points. So basically, I just wanted to say that we have written a piece of software called Cluster Finder that allows you to harvest data from mass spec data from mass spec data files that have these patterns in them, and it will find every single one of those patterns. The speed with which it does it depends on how deep you want to go. We find we really don't have to go that deep because we're excluding noise. We get such clean data. So anyway, this first tab collects all of the experimental design and organizes the data. The second tab provides tools to examine the spectra. The third tab, C, does an automated non-targeted analysis, and that's where you're actually finding all the patterns. And then the fourth tab, having found what you believe to be all the compounds you want to look at, this is what is referred to as a sparse data set. It means that you will find a compound in 3 samples out of 10 or 3 samples out of 9. And what you really, and so it because you've only found it in 3, you can't comment on the remaining samples. So what you really want to do is you want to take everything that you're interested in finding and then turning that around, writing out a library, and then doing a secondary search for every single sample, returning the direct answer. Is it or is it not in this sample? For some reason, it wasn't found in the first search, but this time we're going to loosen the parameters and we're going to run a deeply targeted search, and for every sample, we will return it is not present or it is present. And, so this is the only time, so this is a complete data set, non-sparse data set. And we think it's important to have these things. And of course, isotopic ratio outlier analysis is what we're calling the basic pattern. We're really looking for the ratios and using the ratios between the isotopes, between the C13 and the C12. Based on this, we have 3 basic protocols, and I'm going to talk to you about a combination of these first 2, and I'm really not going to discuss the fluxomic approaches, but the basic protocol is the one I've been discussing. This is wherein you have triply redundant information, incredibly strong, very hard to break, almost impossible to get it wrong, and can find, signal, through incredible noise. And then we have phenotypic, where you still have the same pattern on the C13 side. So this is an internal standard that you have added to a sample a biological sample that you can't necessarily label. Say, for instance, a human, or, a corn leaf in a field. There's no way you're going to label a human or label a corn leaf in a field. So it's going to be natural abundance. It's going to be 1.1%. It's not going to have this beautiful pattern over on this side. It's going to have that little stub that tells you that it's 1%. And that little stub may be a hindrance to you, but the fact of the matter is you still have 2 signals. You have the exact mass of the monoisotopic. You know the number of carbons from the height of this, and so you know that if you know exactly where the peak is that you're looking for. You know that the peak is at 175.1190, and so this is at least redundant information. You have 2 points that are verifying that that is in fact the data point that you are looking at. So again, it's a very strong signal. And again, because these signals are so strong and so easy to find, they exclude all non-signals. All signals that are irrelevant to your experiment are, by their very nature, seen as the artifacts that they are, and they're simply not examined. And so it gives you 0 false data is the way we believe it actually looks. So let me approach that topic from a slightly different point of view. How much data is data? I frequently see people running metabolomic systems and reporting that, in this sample they found, one guy was telling me he found 40,000 peaks in every sample. And yeah, I mean, it's okay, he has data on 40,000 peaks, but how much of that is real? And the reality is very easy to determine. If I take some biological and I isotopically label, in this case it was yeast, I grow up yeast on glucose so that and I grow it up for, 30 generations. There is no C13, there is no C12 anywhere near these yeast cells. So I know that every one of these yeasts has been, every molecule in the yeast has been isotopically labeled. And I insert that and I analyze that, then I know that everything in the material that I'm putting into the analysis and trying to analyze is going to be isotopically labeled. So that's the experiment. I do that, and I run it through a standard program that we have all used at one point or another, MZMine. This is what probably 80% of the people still use. And I found 3,200 peaks. And this is how the guy reported 40,000 peaks. I set my criteria for finding these peaks relatively high at 100,000. So I'm not even going into the dirt. But I found 3,200 peaks. The cluster finder program, which is now going to exclude artifacts, it's only going to find those things that are that exhibit isotopic label. And in other words, is only going to find those things that were actually in the yeast, finds at the same setting 100,000, 781 peaks. That's telling me that the difference, that most of these peaks, in fact, 74% of these peaks, are artifacts. They're not coming from my biological sample. That's huge. You know what the statistics of finding a false positive within those artifacts is? It's destructive to to the basic metabolomic processes, and something we really need to pay attention to. So the majority of the features found are artifacts, and we just automatically remove artifacts because we don't believe that they have any place in the analysis. And there were a lot of other findings, and among many biological peaks are known compounds, and that makes perfect sense. But there are still a lot of unknown peaks. And then the real question comes up, and this is a hot topic that I'm sure you've hit already. What are these unknowns? In the first place, the IROA patterns actually help you identify the unknowns, in the sense that every time you have an IROA pattern, the number of carbons and the monoisotopic masses give you unique formulae. And so therefore, or it gives you a unique formula. So you always know the formula for any IROA peak. You may not know the compound if there are more than one compound associated with any particular formula, but you know the formula and you can't get that wrong. Most unknown biological peaks we find to be fragments, adducts, or polymeric species. They're things that are happening inside the mass spec. And so we've actually built into our software a fair amount of time and effort that helps us sort through, these unknowns and identify them as to, what their relationship to anything else is. And so we find that there are still, some true unknown unknowns, but most unknowns are really, variants of already known peaks. Anyway, that's just back to basic metabolomics. Now, this is the process that we've been most recently enthused about, and we are calling this the IROA TruQuant IQQ, where IQQ stands for Identify, Quantify. Yeah.
We have a question. Could we?
I'd be happy to. Sorry. And Steve, if you could relay the question, because I will not be able to hear from the back.
Well, if you would come up to the front and ask your question. So this is Tatiana.
Okay.
Hi, Chris. One question. Could you elaborate a little bit on the mathematical model? I see that the peaks, the mirror images are not linear. So that part is clear, but I would like to know if it's based on Bayesian statistics or Green's functions, or just a little bit more on the mathematics side.
I would be happy to. Thank you for the question. And so it's actually very simple. Realize that it's a statistical process, and the statistical probability is what's driving it. So it is a binomial distribution in which it is which the X and Y are the two percentages of the mixture, 95 and 5, to the nth power, where n is the number of carbons in the molecule. And with that, it actually falls out extremely simply. Does that answer? So it's a binomial equation. Steve?
Yes, she can come to the front again.
Okay, so let me get this straight. So you are using a binomial distribution mixed with a power law, where the power law is fit to the 95 and the 5 in the example that you gave, for example.
Yes. So I've just changed the slide. Please stay there. So we can continue the conversation. So I've just changed the slide. This is, normally we think of a standard distribution, which is a binomial distribution of a 50-50 mixture. This is a binomial distribution of a 95-5 mixture, in which n is controlling the height of this. So if you look at that distribution, you actually see that it just falls out. This is the only peak. The m+1 peak is the only peak in which n plays a significant simple role, and it is that simple role that gives you the step function. But it's a very straightforward binomial distribution, simply because you have, by kicking up to 5%, you've effectively removed all of the other isotopic influences. So there would be isotopic influences from deuterium, oxygen, nitrogen, other isotopes, but they are all so far below 1%. This becomes absolutely dominant once you move it up to 5%. So effectively, the others become unimportant, and this becomes the sole driving factor. And so it turns out, this is trivial to solve and actually very easy. But the key here is that it's a probability function, just like a binomial distribution, but just like a Gaussian curve, which is a 50-50 curve. This is a 5-95, and the other one is a 95-5. I mean, they're just reverse, but it's a straight binomial.
Right. One last question. So since this, since you're fitting to n, where n relates to the height of the peak, and the peaks are not symmetric, so this is a nonlinear function, there is a very low probability, theoretically.
And I'm sorry, let me just correct you for a second.
Okay.
The n refers to, the n is the number of carbons in the molecule. It's so statistically, what the number of what n refers to is the number of times you flip a coin, if it was a 50-50. But in this particular case, n is the number of carbons, because each carbon represents a different probability event. And so what you're looking for is the sum of the probability events across all the number of carbons in the molecule. And we are assuming that all carbons have the same 5% probability, simply because they were grown, the material is all grown biologically on material in which we have controlled the carbon percentages. And so this, in fact, mathematically, we find it, most molecules do fit the rule pretty closely.
Okay, yeah, that was
within the
question.
nucleotides, you can be.
Of little error, but thank you so much. It's very, very, very nice. Thank you.
Okay, thanks.
You're quite welcome. Good question. Okay, so we were talking about IROA TruQuant. The TruQuant stands for identify, quantify, and qualify. And so we believe that the other major problem with metabolomics today is, people don't really have good identity in the molecules. They take a mass and they throw it against the database. And quantification, I'll show you that problem. And qualify, people, it's very hard to track the quality, the performance of your instrument. So we have a system which uses two standards: a long-term reference sample, the LTR, IROA LTRS. It's a long-term reference sample. It's always the same, and it will be always the same for the next few years. I mean, 20 years if you want. It is a yeast extract fully labeled at 5% and 95%. So it is your triply redundant system. It provides the I and the Q. It provides the identity and the quality, and that is a complete QA/QC for your runtime experiments. And then we have a second part, the IROA IS, the internal standard, which is spiked into every experimental sample. It is exactly the same as the 95% that was used here. It is exactly the same material. And it is provided at exactly the same concentration. So the height of this peak is the same height as the height, it should be the same height as the height seen here. So we know that we can find it, and it provides the second Q. It provides the Q of quantitation. Again, this is how it works. You have your experimental samples. They have natural abundance peaks. You have your internal standard. Your internal standard has these 5% shaped peaks. You add them into each sample so that now your experimental samples always have the natural abundance compound plus the 5% internal standard, and that is present at 20 micrograms C13 internal standard per sample. And then you have this other sample, the long-term reference sample, and the other sample has, again, 20 micrograms of the C13IS per sample, but it also contains the 5% equivalent molecule. And so this is a triply redundant system in which you can search for every compound. And here, the fact of the matter is, these are both present at 5%. And so we can use not only this triply redundant stringency, but we can enforce one other thing. We expect that the height, the symmetry of these system pairs should be fairly high. And so we, in fact, require that they also be symmetrical peak systems. And so we can find these with great precision through unbelievable muck and noise. And there's a lot of it in the mass spec. And furthermore, we can find these things. And because this is not a system we intend to really quantitate, we're only qualifying sample things over here, we can afford to take some time off from the instrumentation and allow the instrument to be doing other things like fragmentation via a mechanism like swath, or ion mobility using something like DSQ or standard IM. And we can use these secondary features to give us absolute proof if the formula that you get for this from this peak is not definitive to a single molecule. So if this is not definitive, then the combination of this plus this should be definitive for every molecule. To date, we believe it is. So you run these samples, these with swath intervening scans, these only in full scans. You run these two samples randomly intermixed with one another And you now have a system in which you can be assured you're doing your untargeted search on this sample. You find all of these peaks, write out the library for that day using the dirt. Your columns are a little dirty, so the chromatography shifted. You write out a targeted search that you apply to these samples, and it now returns for these samples a complete data set for every compound that you found in the LTRS, including, and this is the important part, including internal standard found, 0 of the natural abundance found. Most of the time, and when you are reporting a 0, you don't report a 0, you report what is referred to as a null value. A null value means that you don't know. And here, we can actually say, we found the internal standard. There was 0. So our zeros are real zeros. So, again, it's all in the case of getting better and better data. Let me talk to you about identification, and I'm going to do this quick because I think we're running out of time. So we're pulling the formula from, this is all coming from the LTRS.
Chris?
Yeah.
Just to let you know, we have up to 45 minutes, so.
45 minutes left?
Yeah, as long as this conversation wants to go on.
Oh, good. Okay. Well, but I'm still going to go fast because I like the questions. Anyway, we're pulling the formula from the basic peak. We're pulling secondary data from either the fragmentation, which in swath gives us IROA peaks, and because they're IROA peaks, we actually have formulae for every one of these peaks rather than just masses. And since we have formulae, we're not going mass on mass. We're not doing a dot product search. We're actually, saying, yes, I see, each one of the pieces as a named piece. Or the ion mobility, where the ion mobility is a qualifier. But these things are giving us very strong, very competent, very verifiable mass spectral information. And here is, I've got, this is what we're doing. When we see these peaks, we of course can tear them apart and apply formulas to every single one of these fragments. And it just happens as a matter of course. Ion mobility does the same thing. In ion mobility, if 2 molecules are coming through at the same time, they will actually separate out in the drift tube. And so since they will separate out in the drift tube, we get to see the different curves for overlapping IROA peaks, which is sometimes quite useful as well. It allows us to verify very complex situations. But again, what it ultimately does is it allows us to put very strong, verifiable nomenclature assigned to every peak. If you have a formula that is verified from the basic peak and a secondary characteristic such as fragmentation or ion drift, I think most people would say that the probability of your getting the identification wrong is pretty low. And that's what it's all about. You just want to get better. QA/QC. Why does the LTRS give you better QA/QC? And the LTRS is injected randomly, but let's say about every 10 to 12 injections. The LTRS never changes. It's always the exact same material. It's always brought up in exactly 40 microliters of solvent. And so it doesn't change. It's also relatively simple. Relative, if you consider something that has maybe, less than 2,000 compounds in it. Simple. It's relatively simple. So it's not like blood plasma, which is what a lot of people use, and this should always be the same. So since you're injecting it every day, 3 to 4 times, we'll expect to see the number of IROA paired peaks. If you see 800 most of the time, sure, you're going to see a standard distribution around the 800. But within that standard distribution, you will not expect to see something like 700. And if you start seeing 700, then, there's something wrong. Something is just not working. And so the number of peaks that you see is a QA for the sensitivity of the instrument on that particular day. The retention time for every compound. After a while, these compounds never change. So if you see phenylalanine out here at, say, 5.6 minutes, and all of a sudden it's dropping down to 5.4, but it won't matter to the experiment because you're going to write out a library and run a targeted search on where it is running today when you're analyzing the physical samples. But it is giving you information that your column is reaching the end and needs a good cleaning. So you have a QA on the chromatography that, as long as you're paying attention to it, will help make sure that you're always running high quality data. One of the other things I mentioned earlier was the fact that, in that experiment that where we, we're trying to figure out how much noise was noise, we see a lot of, became aware of all of the in-source fragmentation activity. And the in-source fragmentation activity is sensitive to, such things as, the size of the capillary, the dirt in the capillary, the power on the skimmers. It's minor, very, very minor details within the source that are controlling this. And they don't change a lot, but they do change. And when they change, it's pretty important. So, for instance, we measure the phenylalanine always loses a carbon dioxide, actually a CH2O2, and that loss is always seen as a peak at 120. So we measure the ratio of the 120 to the 166. Is the phenylalanine breaking down at a greater than normal rate? And we think that you want to know that, because if you know that, then you know that maybe you should be summing the 120 to the phenylalanine native peak in order to get a quantitative result, because that 120 peak represents a certain percentage of the phenylalanine that's actually in your sample. Most people tend to ignore the fact that, they think it's a constant, but it's not a constant. It has to do with source. The total signal found for all compounds, we find is actually a very good QA of injection accuracy. You're making injections of 2 microliters. 2 microliters is pretty small. And the fact of the matter is, if you believe you can make a measurement, an injection of 2 microliters that is better than plus or minus, say 7 or 8%, I would suggest you should measure that, because my guess is injection accuracy is, you just want to make sure that your injector is doing what you think it's doing. I've seen needles get fouled, and so the injection is not completely made, the correct amount of material is not sucked up and it's not delivered. And, so we think total signal for all compounds, the total signal of everything seen in the mass spec, which is what this picture is if that total signal should remain constant, it's always the same. And so if you're making a 2 microliter injection of this mixture that's been brought up in 40 microliters, it should be the same. So this gives you a lot of QA on the process and on the instrumentation. Quantification, I'm going to show you what I think is one of the other poorly understood areas for inaccuracy, and that is suppression. You know, when I began, I used to think that suppression was really not that big a problem. And I think I thought it was not that big a problem because there was no solution to it if it was a problem. I mean, there wasn't anything I could do about it. I hadn't figured it out. And I think we've now figured it out. And we figured it out. The way to show you this is this very simple experiment. You take a large single extract of plasma was made, and you know, and then varying quantities of the extract were delivered as triplicate individual samples. So triplicate from this one extract, which is chemically identical, it's homogeneous. You know, so 3 50 microliter aliquots were made, 3 75 microliter aliquots were made, 300 microliter, 150 microliter, 200 microliter, and 400 microliter aliquots were also made in triplicate. And so we know that for every compound in them, we know exactly the concentration of every compound in them is going to follow a curve that looks like this, because it was a homogeneous solution that was put in. So we expect to see, when we look at every compound, we expect to see a straight line going that will be sloped like this. On the other hand, the C13 signal, the samples were all dried down, and then they were brought back into solution by the addition of 40 microliters of the internal standard. And 40 microliters of the internal standard, this is again a homogeneous solution. Since every sample received 40 microliters, we expect that the linearity will be very different from this linearity. It will in fact be constant. This is, after all, an internal standard. So what do we actually see? What we actually see is this. We see for the C12, we see it starts off relatively linear and then very quickly deviates. For the internal standard, we don't even really see it starting off linear. We see it dropping from the word go. On the other hand, the ratio of the C12 to the C13 peaks, because of course both of these are labeled, I mean, one natural abundance, C12, and one isotopically labeled, the ratio is exactly the line we expect. So we know that the ratio is correctly reporting the concentration. Not that big a surprise. Every analytical chemist in the world understands the reason you put an internal standard in is to get an accurate measurement, and that the accurate measurement will be derived. But we took it one step further. We said, what is going on here? Why is this not linear, which would have brought it up to about here? And the answer is, it's suppression. The internal standard is being severely suppressed. It's going down dramatically. So we thought about it and we realized that the internal standard is in fact a number that we know. We know what the lowest value, the least suppressed value for this is, and we know that the ratio is correct. So we can synthesize, we can correct suppression we can correct suppression. This is what we expect to see. This is what we expect to see on the C13 side. The blue is what we actually see on the in the internal standards as seen in the mass spec, and the red is what we can correct them to by assuming they are constant. And then this is what we find if we take these values, ignore them, but rather multiply this value by the ratio. And at that point, we regain linearity, and we have effectively corrected for suppression. Not only have we corrected for suppression, but now for the first time, we can actually calculate the level of suppression at any given time and place. And that's another story. But let me carry that through to the fact that if we took every sample that was, every compound that was in our samples and looked at suppression, remember, I used to believe that suppression was a relatively, benign, low-level event that occurred in some compounds, but not many. And every compound showed the range of suppression that we saw in every compound that we measured in this experiment was between 6% and 92%. No compounds exhibited less than 6% suppression. The graph of the distribution of the suppressions, you will notice centers at around 40. And it runs 50% of the compounds exhibit suppression between 25% and 55%. So that means that almost, half of your samples are exhibiting suppression at, greater than 25%, and that some of your samples in this tail are even worse. That's what this curve is about. I noticed that some of the samples in some compounds actually were negatively correlated with the amount injected. In other words, in the higher, there was a negative correlation between this peak and the concentration. This line slopes down when in fact it should be sloping up. The more you inject, the lower this peak goes. The suppression level here was 91.8%. Turns out that anywhere above 80%, you have this negative correlation. The peaks will actually go down as you increase the concentration of the molecule injected. So unless you are correcting for suppression, you can tell a difference, but you can't tell, you're wrong in the direction you think the difference is going. And furthermore, in the range from, about 60 to 80, they're perfectly flat. The more you inject, this peak doesn't, it just becomes linear. The response is almost independent of concentration, and it's just, so you really have to correct for suppression. Anyway, once we sort of understood this, you put the internal standard in, and the internal standard allows you to correct for it. And so we can, therefore, raw signal is black for the C12. The corrected signal for the C12 is shown in green. Green is exactly the curve we would expect. The raw signal for the internal standard is shown in purple, and it is going down, again, exactly what you would expect. I mean, you can see the suppression, you can see the effect of suppression in all of these. But you can correct it, and you correct that back to what it should be. And we realized that once you had corrected it, some very significant things came out of this. Once you have corrected for suppression, you can now normalize your samples against one another. And that was actually what this experiment was designed to explore, was the normalization, the ability to take samples of different sizes and correct for their different sizes. Because when you take a biopsy out of the freezer, that biopsy is, say 8 milligrams. But 2 of those milligrams may be water that has frozen onto it, before you got it on the scale, or it may have lost 2 milligrams if it has had time to thaw and the water's had any chance to evaporate. Most labs are warm. So, the size of the biological samples I'm familiar with, you have to take them with a grain of salt, and we do. But I also have always thought that if you could normalize your samples, then that would be a huge benefit. And we now believe that if you take the total area under the curve for any of these samples and the total area for any of these compounds, the C12, and the total area under the curve for the internal standards, and you normalize them, you mathematically multiply them so that the 2 total areas are 1 to 1, then you have normalized the samples. This is not our invention. This is a technique that was published in, I think, 2008, and is a reasonably well understood technique. He was using it for urine values, mustus, but he never had an internal standard. Here we're doing sort of a double mustus, and the normalization is perfect. So if I take these samples, 50 microliters, 7,500, 150, 200, and 400, and I normalize them as I suggested, I end up with the blue dots, and the samples now look as if they were all of the same size, despite the fact that they were not. Now, this is not all these samples are identical, so I wouldn't expect a real-world experiment would come out this perfectly, but I do believe that the normalization is a good thing. Secondarily, there's a very interesting outcome of this experiment, and the reason to do it is to understand where this line, the line that represents the total signal from the C12, crosses this line, the total signal from the internal standard. Where that signal crosses is where the optimal value will be for having a 1-to-1 mixture of your experimental sample with your internal standard. You just have to do this once. Once you understand the SOP you follow gives you a value of 350, which is effectively what it gives you, then you simply always stick with your SOP, and you use a sample size of 350 microliters, which most people usually have, and then and you will get the optimal readout for every one of your samples. Having said that, we can certainly we could apply all of the same rules and look at any one of these samples, even without normalization and even without doing this. The ratios are going to give us the correct values. The only thing is, with these much smaller samples, we will see fewer compounds, and with these larger samples, we'll see more samples. So, but once you know that you adjust everything to 350, you're going to get sort of optimal results. And so that's really where we are. Oh, I mean, one thing, we can also look across platforms, since the LTRS always has the same number of compounds, and they're always the same. A certain number of them have unique mass. The compounds in them have unique masses, so those are very easy to map from one chromatographic system on one instrument to another chromatographic system on another system. And the isobars, if you have any of the secondary physical phenomena, either swath or ion mobility, then you can always map from one system to another using the LTRS, and then your quantitation and the quantitation is of course always going to be the same compound for compound, because the internal standard is always present at exactly the same concentration as is the LTRS. And so with that, my summary, it's a robust system for reproducible peak identification, peak quantitation, and a daily QA/QC for instrument performance and process control. We think metabolomics needs this stuff. The long-term reference sample directly provides continuous runtime performance. The reference sample provides cross-platform comparisons. The long-term reference sample provides the basis of a validated chemical identification system. The internal standard contains all of the compounds in the LTRS at exactly the same concentration and provides for absolutely reproducible quantitation, because it's always present at the same, just like any internal. It's a good internal standard. And what maybe people did not realize, and we are now pushing, is that the internal standard provides a mechanism for suppression correction. And once you have corrected for suppression, sample to sample normalization becomes possible. And so, we just think this is a mechanism for getting better quality data. We believe in metabolomics, and this is a contribution towards better metabolomics. And with that, I thank you, and am happy for any questions.
Okay. Thank you, Chris. It's very, very interesting. I'm sure you've seen the transition from what we've been describing in class so far into something that's really, it's a big step up. Now, Chris has been working on this for a number of years, and I've actually had him come to UAB three times, Chris?
Yes, I have.
Yes, as part of the workshop. And it's been hard for people to actually engage the community, but we engaged my staff this last year. Chris spent quite a bit of time with them, and we've done some preliminary experiments. We were actually at the time had a really bad LC system, which but nonetheless we still got data that was very, very interesting, and we're about to embark on a more systematic evaluation to verify for ourselves in this lab that all of this works. So I'm sure you have some questions. I mean, you ought to have. And some people automatically ask questions. So Zdenek, would you like to come up and pose the question?
So thank you, Chris. Thanks so much. This is super exciting. I can't even describe how excited I am about this.
Thank you.
One question for both of you. When is this technology coming to UAB, and when we can use the full potential of it?
It's there now.
Yeah.
Hey, can we do it?
As Steve just said, we had a teleconference on Monday to plan out the next series of experiments. We had tried to do this last fall, but I think as Steve said, the chromatography was flawed. So that's now been fixed.
We were down for about 4 months. The nano LC system was just changing all over the place. And we had engineers come in, engineers come in, engineers come in. And fortunately, they told us never to go inside this box. But they went inside the box and left the cover up. And this allowed Landon to, with his very sharp eyes, to look for things that weren't right. And eventually we found what the problem was and how to fix it. So now we've got reproducible nano LC back again. And so that was why we chose to re-engage with Chris, because we were ready. We thought that this was very, very important. And we wanted to connect our evaluation here to get ready for an S10 application, which is due May the 31st. So when I leave this meeting, I'm going to be talking with Maggie Christian from SciEx to arrange to go to SciEx to actually do what we can do here, also do it on their new, latest, greatest system, which is much more sensitive than what we have. Our current instrument is almost 10 years old. And the system up there will also have the iMobility capability, which we don't have on 5600, but we do have on our 6500.
So can we do this right now here?
Well, I wouldn't want to take your experiment tomorrow because we're going to do some systematic experiments that we plan with Chris. But the idea is that if these clearly work, and we've got enough data to suggest they will, even on the cruddy system that we were working with back in the fall, the correction that you saw for the competition between the ions was clearly corrected, and we got a perfectly linear curve. We actually took a really horrible matrix. So the matrix was squeezed urine out of the cover bun of a newborn. So we've been doing some experiments with pediatric people wanting to measure F2 isoprostanes in newborn children. And so we evaluated different ways in which we could collect it. And one of these was in a cuddle bun, which is like a diaper. And so it was squeezed diaper fluid. And we put the internal standard that Chris has talked about into this and measured the compounds that we could see in this urine, corrected for by the interference that was measured by the carbon-13 signal. And we got a perfectly linear curve once corrected. When you saw the data, Chris can't see it here, but I'm sure he's seen many of these. As we added more and more urine, the signal went up, rapidly became nonlinear, reached a peak and started going down again. And of course, exactly the same thing happened to the carbon-13 internal standard. And when corrected, we had an R value on the corrected of better than 0.99, even with the cruddy system. So,
do you have the analysis software? The analysis software was shown. The analysis software.
The software, yes, or Chris is going to give us this is constantly evolving. Chris, that's right.
Yes, and I can barely hear the questions, but I can hear your responses. So I'm sort of following.
Well, the question was, is the software available?
The software is freely available to anybody who can use it. And you have to listen. Any piece of software takes a certain amount of learning to learn to use. We think Cluster Finder is reasonably intuitive and therefore easy to learn. But unless you're, going to bother, we tend not to hand it out because then, but we give it away for free. Having said that, the software is also constantly evolving. So for instance, the suppression correction was something that we only figured out, I guess last year, and we revealed that at last year's ASMS, and then the normalization, we had not yet completed all of the work on that, until we got to the Metabolomics Society at the end of June. And we have we're continuously evolving new algorithms. We constantly scan the literature, look for things, and but I think at this point, I'll tell you the dirty little secret is that this year we're going to be providing a module. We can't suppression correct for a compound that is not isotopic, but we have come to believe that if we can at least normalize the samples correctly, then we could get better data for even those compounds that are not isotopically balanced, for which we do not have an internal standard. And so the next evolution in the software will be, you know, the normalization of what we call C12 orphans, and that will be, I think, another step forward in the quantitation, because I think the normalization is good. The normalization, I now believe, is doing exactly what it should do. So we're constantly evolving the software. So the software we release is really only good for about 6 months, and then it will automatically shut off. And it's because if we find a solution to a problem, we want you to be using the most recent, but we give it away for free.
So if I understand correctly, Steve, you are saying that we need a new machine, more sensitive machine, to fully use this potential, right?
Yeah, to expand the potential of this, we need more sensitivity. So we currently have a 10-year-old machine. We got with an S10 grant in 2009.
Right.
So
what I'm thinking, so as we discussed with Steve yesterday, the cancer center is actually interviewing 3 different people with expertise in metabolomics, and they want to do that. But we should connect this recruitment effort with commitment to support the S10 application and the institutional support for the service for 5 years. Otherwise, we will never get it, right? So we have to make sure that we obtain this machine, and we have to, you know, we have to engage the faculty to make this into the administration.
Okay, that's another conversation for later. Student, other questions that you have about this? Because this is, you know, it's different. It's taking us to a much higher level. As Chris said, it's really like the evolution that's occurred in many of the omics techniques. You know, I spent a lot of time working with microarrays and looking at how the microarray data depended on the year that you actually got your software from Affymetrix from. Taking the same set of data, the same set of raw data, would do a different interpretation each year. And then eventually it stabilized because the field got better. And then the technology changed again and went to RNA-seq. And I can't comment on RNA-seq because I don't have practical experience using it. But the whole field is moving. Every field is moving to better and better ways of doing things. So, question.
So my question maybe is a little more on, I guess, the use side. So the cluster finder, I can see where that works really well if you have the 2 labeled kind of basic approach. But if you're looking at the phenotypic approach where you have a human sample, how well does the cluster finder work at kind of identifying and matching those, I guess, the labeled peaks with the sample peak?
Thank you. And I think the question was, and I'm saying this because I could barely hear you, but I think the question was, how good relative to the basic protocol is the phenotypic protocol using cluster finder, and if I could discuss that to some extent. You're absolutely correct. The triply redundant signal, because of its very nature, is incredibly easy to see. But consider the following experiment. I'm looking at a biosynthetic organism that is producing drug A, and I am doing something that is turning on or off the genes that are controlling the production of drug A. In some samples, I will have no drug A, and in other samples, I will have drug A. So I am sometimes going to be returning a 0 value. Cluster Finder in the targeted search does not do as good a job returning a 0 value. It cannot do. No software can do a good job returning a 0 value in an unbiased search, because it's the nature of the beast. It cannot prove it cannot prove a null. You know, and that is truly a null, and that is why we have set up the search pattern the way we have. We run an unbiased search over the course of the entire experiment to hope to find any situation in which there is both a C12 and a C13 in, and then you choose the number, at least one sample. And then if you say, I want to find every sample that contains this compound, even if it did not meet the exact stringent relations, that's why we run the targeted analysis. So our process is really meant to find everything that is significant, and then run every compound that you want to know about, and then run a targeted analysis in which we always find the internal standard. And then, having found the internal standard, we actually look and quantitate for the existence of the natural abundance peak. We think this is probably as strong a position as we can get to. In the beginning, we used to think that we could do the same thing from the C12 side up, but we realized that it became unworkable, and so, and it's much better. It had to do with the fact that there is, despite what we would like, there is an isotopic shift in the enzymes that are in humans. The literature actually says that most enzymes are agnostic to isotope weight mass, and effectively it's true. We're looking at an 8% mass difference, for C12 to C13. So, that's a small enough difference, and as humans, we've learned to live with 1.1%. So most enzymes are perfectly capable of making that jump. However, there is just enough of an effect that we find that the internal standard will always be a little bit different than the 5% or the natural abundance. And so therefore, we've chosen to argue the other side, where you are simply using the C13 as a representative internal standard, and therefore we focused all of the cluster finder software on the C13 side and not on the C12 side, where we could find a compound that existed, say, in C12, but did not exist in C13. Did that answer the question? I think I know what you're asking, but maybe I didn't get it.
No, I think that's good. But I guess another question that I had is, when you're looking at, so you're labeling in yeast, but if you were to label in like a human cancer line and
Absolutely.
Under different conditions, does that give you kind of a better metabolic profile to work with human samples than a yeast labeling would?
Much better. Yep. No two ways about it.
So then you want to be kind of as close as possible in your cell line choice and grow it just under kind of multiple conditions as far as like glucose and different nutrient availabilities, and then kind of mix the metabolites from each of those to look at a standard?
Absolutely. We, in fact, actually make it much easier than that. What we spent, as Steve said, I've been working on this for a long time. In the very beginning, we started making media, and we were, all of the early work was done on media with people growing their own cells or growing their own, organisms, or growing whatever they wanted to, and we provided media. And I think we have a very good, rich, mammalian media, media for growing any of the NCI 60 cell lines. And, and I say that because they tend not to require too many exotic additional things. And it works like a charm. The cells grow up, but it's a more expensive proposition because you will have to grow the cells yourself, but the cells will be biochemically unique to what you want, and but it may cost you, maybe 100 times more because you're going to have to grow those cells in large enough volume, and the media is more expensive and everything. We've moved to this this TruQuant, which is it is correct. It's a yeast-based system because in terms of primary and intermediary metabolism, it contains most of the compounds that we care about in humans. It doesn't contain them all, and it doesn't contain them in exactly the same proportion that you would like to see them, but it does a very good job. The main thing was it's so cheap. It literally costs it's going to increase the cost of the analysis by less than 0.5% of the entire cost of the analysis, which is huge. I mean, it's effectively a free add-in that you can do to any sample set, and it just helps you boost the quality of the work. I wish we could find a way to grow mammalian cells, inexpensively enough to do the same thing, but to grow, say, a CHO cell, which is the easiest cell to grow, would probably still cost 10 to 20 times as much as a yeast.
So perhaps another question those who want to do metabolomics might ask, what's the cost of the internal standards that you use? Hundreds of dollars a time? $5 a time?
No, it's probably about $1.50 a sample.
Yeah. I was setting you up, Chris.
Okay. The LTRS I think is free, and it all comes as a kit, but the kits are for 90 samples at a time, and I think they cost $150. We're really, we want it to be used. Yeah. I mean, from our point of view, we're selling it, not that much above cost. We're not exactly making money, but the key here is that I think we would like to see metabolomics not fail.
Yeah, exactly. And I think metabolomics has come a long way. The class have heard me talk from my rationales, so I won't repeat them. But the human is much more than the genes that we have been studying, and so there's a lot of compounds that get into our systems, and I guess that that's something in the future that we might want to label some of the compounds that come through the diet that are not the ones that are in the human.
Well, and we actually do have a mechanism that's probably going to come online in not this year, but next year, that I think will approach some of those topics.
So part of the botanical center that we had here at UAB, which was joint with Purdue for 10 years, we managed to develop cell culture of plants. So we could actually grow plant cells in cell culture and label them with anything. Our main goal when we did this work was to label with carbon-14, not because we were measuring radioactivity, but because Purdue had an accelerator mass spectrometer that could measure one carbon-14 atom, 15 carbon atoms. And it became a way to increase the sensitivity of monitoring the carbon compounds at levels that we just couldn't do. And this was basically a Cold War instrumentation that was developed. There's only a few of them in the country. There's one at Lawrence Livermore National Lab, and there's one at Purdue. And it enabled us to measure the movement of a carbon-13 labeled plant product through an animal's body and into the brain, and actually microsample the brain and see the arrival of this compound. So there's all sorts of games that could be played with plant cells to make unique compounds that are part of our diet. And so we can talk about, I have several people who are involved in that and still working on that. Yeah, we can talk about that later. Any other questions before we finish? I think maybe stunned, maybe excited, maybe confused because I haven't quite read it all. But
well,
it'll be good for them to follow up. If you have any questions, I can give you Chris's email. I know
please do. I have provided all of the slides that I used as a, I believe you recorded this. I provided this as a PDF, and please feel free to write me with questions as you look at it and new questions arise.
I think if people are planning new grants in metabolomics, these are the sort of things that you need to write in, because I think it's going to give anyone who uses this a real step up in terms of data quality. You can make a lot of statements about data quality using this methodology that is not available in most labs at the moment. Now, hopefully that will change. And I know that's Chris's ambition. So thank you very much, Chris. Again, I think everything went well after a little bit of help from my colleagues here. And we were able to hear you clearly. And thank you again.
Good. And thank you very much. Have a great day, all of you.